Hey, what's going on, guys? WukongJS here. In this video, I will try to explain the gist essence of so-called TEXEL'S tuning method, which is the method of automated evaluation tuning in chess engines. Just to give you an idea what a rocket science it was to me, it took me kind of several months in order to put all the things together to finally realize how it works, to understand the logic behind it, and to come up with a particular implementation that is actually kind of working. I didn't really make enough tests because it's really time consuming, assuming the very basic implementation that I currently have. So it's quite a bit too early to say about the actual results, but this doesn't really matter that much at the moment. So the problem with explanations regarding TEXEL'S tuning in those resources available is if you're not it's full of mathematical formulas. When I personally see a mathematical formula, I just really want to drop the stuff instantly and never ever come back to that, because I'm a complete noob in math and I hate math because I don't know, it might seem a little bit strange that I'm writing chess engines, but still I'm very, very bad. I really suck in math, to be honest. But anyway, so in this video I'll try to provide the so-called code-making explanations on how the TEXEL'S tuning method is actually working, and try to make it as simple as possible so other noobs just like me could have make use of it and actually come up with a pipeline and to establish this pipeline flow to make it kind of working. And again, like I have a client that I'm writing web scrapers for, and he's a data scientist, and once he said that the most important and the most under-evaluated thing in machine learning in general is the explanations of how to establish the pipeline, how to bring all the things together. And he said, like, the problem with all the tutorials in machine learning is the problem is that only some only the parts in separate are described in great details, but no one actually explains how to bring all this stuff together to make it work, while the real world machine learning projects are all about bringing the stuff all together, because otherwise it literally doesn't make any sense at all. And this TEXEL'S tuning implementation can be considered as a real machine learning project, and this is the very first machine learning project I ever came up with. I wish I could not doing that, but I just don't really want to use someone else's values within the evaluation. I really want to generate my own ones to make WukongJS really unique chess engine. So that's the reason for torturing my brain and trying to understand how it works. So I'm sorry for a bit long intro, and let's actually go to the gist. So first I will try to describe the issue. What's the issue? Because without understanding what is the issue, it's hard to realize why this method is actually used, and then we'll go to the explanation on how it works. So if it's already the TEXEL'S tuning code. So I just want to show you guys the source code. Oh, probably can I do it? Yeah, let's just better show you this on GitHub. So here is the source code of my JavaScript chess engine Wukong. If we just go to the evaluation part, the only logic that Wukong uses for evaluation is material weights and positional square tables, and that's kind of it. And the current values I'm having here are the values from RofChade chess engine by Ronald Friederich. And by the way, yeah, before I forgot to give huge credit to Ronald. So without explanations given to me by the private messages on TalkChess forum, I would never ever come up with this sort of understanding and implementation, because the way Ronald was explaining he was explaining it very calmly, as he explaining this to a 5-year-old kid who is a monkey at the same time. So this is literally my case, And only thanks to his patience, I finally managed to pick up this sort of a method, which was literally impossible for me before. So a very quick overview of the particular parameters that the evaluation function within the WukongJS chess engine is relying on. So we have the opening phase and the end game phase margin scores, and these values are obtained by calculating all the material other but pawns and kings. So we're not taking pawns into account, and we're not taking kings into account. Only knights, bishops, rooks, and queens. So say we have 4 rooks on the chessboard, it would be 337 multiplied by 4 plus 4 bishops, 365 multiplied by 4 plus 4 rooks, like 477 multiplied by 4, 2 queens, like 1025 multiplied by 2. So it's not the value for all the pieces, it's the value around, like if we have exchanged a minor piece or a couple of minor pieces. I'm not sure at the moment in particular, so it's I might be wrong. Those just need to turn the calculator and manually calculate this value. So the idea is that when no pieces are being exchanged on the chessboard, then we're using the material weights as well as the p-squared tables to give a chess engine an idea of where to develop its pieces from the pure opening scores. So pure this tables for opening and this pure values for material weights. And exactly the same happens for the pure endgame when there are no material other but pawns and kings on the chessboard. So in that case, we would be using the pure endgame material. The weights are different in endgame, so you see like the pawn is worth more compared to the pawn's value in the opening. So the values are slightly a bit different because the value of pieces in the endgame kind of changes. And also the p-squared tables are also different for the endgame. So just to give you an idea, well, the most easy to understand is the king. So you see like in the opening, king is discouraged from going to the center, and it's encouraged to castle queen side or king side or step aside 1 square here and there and here maybe, but never ever to go to the center. While in the endgame, we instead want to make king moving towards the center, because most likely this would be leading either to supporting the passed pawn that is trying to promote or try to mate opponent's king, trying to avoid opponent's king sticking in the center, try to push it to the board edge and checkmate it there eventually. And so these are all the values that I used within the evaluation basically. And now the most interesting part, that for the middle game phase, so when let's say we have exchanged a couple of minor pieces, but really lots of pieces on board still, so it's not that pure endgame yet. In that case, we're interpolating the values between the opening and the endgame phase. So it means like depending on how much material left on the chessboard, pawn would be deciding either to defend the king or trying to promote. So let's say we have exchanged only a couple of knights. So the values are already getting interpolated. So the values for pawns from the end game already encouraging the pawn kind of trying to start promoting to become a queen one day. But at the same time, if the game phase is not really that deep end game yet, it would rather be considering more would be using these values to defend the king, which is the implicit implementation of the king safety using the bare p-squared tables, and less trying to promote. On the other hand, where by the time when we're exchanging pieces, like exchanging a couple more bishops, a couple more queens and rooks, in that case we're closer to the end game. So this means that we're trying to so this values starts getting less influential. Instead, these values are getting more and more influential. So the closer to the end game, the more it kind of relies on these values. And the interpolation is the way of the soft transition between the values of the pure opening, sorry guys, right over in here, and the pure end game. Sorry, right over in here. So just to give you an idea, regarding all the values that are about to be tuned using the TEXEL'S tuning method. So in my case, all these values is 794 values. The only thing that we need to subtract are the values for pieces for the opposite side, because if we don't do this, the algorithm would still be altering them as well, and this would be leading to imbalance of the weights for white pieces and black pieces. It's also interesting thing to experiment with, but I just dropped this because I don't know, I just dropped that. So now the problem is, the next step, the issue definition. So the more precise values we have been defined within these tables, the stronger play we have as an output of our chess engine. So just to give you an idea, so if we will use some values like, say, just let me open another window here. So let's say if we use the values which are logical in terms of the general considerations of where to develop the pieces in the opening and the end in the end game, but at the same time these values are kind of taken from the head, like in this case what I've tried here. So we generally want pawns to promote, but at the same time we want them to defend the king. We want to try to go to try to conquer the center. For knights we want generally placing knights in the center and try to avoid placing knight in the board edge and in the corners especially, and so on. Well, for the bishop, so here are the values, like kind of completely handcrafted values taken from the head, from other sources, from some ideas. So trying to put the rook on the seventh rank and so on. So these are the scores from the white player's perspective. So this results, I can't say for sure, but it's around 150 elo points weaker compared to these tuned values here. So you might wonder, like, why is this so influential? But this is all the magic behind the TEXEL'S tuning. So just to give you an idea why to do this. So if you have this symmetrical values taken from the head, and again, the problem is that it's not a problem to give an overall idea that we want to increase the score when the pawn advances, or the relative values for pieces is also seems to be constant. But here the values are symmetrical, while here they are not. And in the real game of chess, not symmetrical values, it's just the matter of testing it. They work better, much better than the symmetrical values. And also, you see, like, these values are like all 50, 20, 20, 40, 40. So there is kind of some sort of a system within them which actually downgrades the playing strength. While if we have a look at this real data set, you see, like, the values are very, very interesting. So they vary quite pretty a lot here. So you see, like, so it's for a knight, let's take a pawn, so it's from 68 minus 11 even on the 7th rank, believe it or not, but here it's minus 11 because most likely this pawn is about to be captured and not ever promoted. Or on the other hand, if there is an endgame when we have king, say, here and pawn here, and the opponent's king goes here, and this is a draw, so it's a bad idea to promote this sort of a pawn here on otherwise empty board. So but it's literally impossible to provide these values from hand, because it's not only the problem to specify the correct values for a single table, but also you need to bear in mind that here are really lots of parameters that depend on each other, especially assuming the tapered evaluation, when we're interpolating the values between the opening scores and the endgame score for both material and the p-score tables. So here is the exact entry point when automated tuning in general and TEXEL'S tuning in particular. Guys, I just want to make sure that actually still, well, sound doesn't matter really that much, but anyway, okay, yeah, just want to make sure that mic is recording. Okay, I'm not using internal but external mic instead. Okay, sorry guys. So here's where the TEXEL'S tuning comes onto the stage basically. So we need not only to find the proper how to call it, basically proper guidelines of where to develop its pieces, but also the most influential parameter, the most influential stuff in terms of the plane strength is the relative differences between all of these values. So we need kind of like tune them all together so they kind of supporting each other. For otherwise, they kind of, it's like they kind of imbalancing the entire engine. So you just imagine a car. So you have an engine, you have a transmission. What else? Like the general, like where you sit, driving seat, this kind of like. So it's the entire mechanism, and the matter of car actually drives. It's the matter of all the parts it consists of. They serve the only purpose of this kind of sort of a drive. I'm sorry for this noob's explanations, but you just try to understand that kind of like engine helps transmission, transmission helps engine, driver helps car. Everything helps each other in order to actually drive. So that's the idea. And exactly the same stuff happens here with these values. So what's the difference between the tuned values and non-tuned values? So tuned values are those values that kind of help each other. And this help, eventually, this results a much stronger play of your chess engine. And on the other hand, if the values do not support each other, it results engine with playing weird moves or playing them in the weird run order or whatever. So it just plays much more kind of worse than when it's tuned. So it's like you're driving on a car where the wheels are about to be taken away, and that's it. Where I don't know, like the engine is going out or something. I don't know. So it's like. It's not even guaranteed that you will get to the destination place if we're talking about the cars. So the same with this evaluation parameters. So the idea behind automated tuning in general and TEXEL'S tuning in particular is to make all of these values support each other, and only in that case this results a stronger play of one's chess engine. So now finally, I'm sorry for such a big intro basically, but without the understanding of the circumstances behind the need of using the automated tuning, it's really quite pretty difficult to understand the particular methodology of how the thing's working, and how this, the implementation, the matter of understanding of the implementation, it's the matter of understanding of the input data that we have and the output data that we have. So probably before actually describing the implementation and the method itself, I would first like to demonstrate the input data and the output data I came up with during the test. Well, obviously the data can be used in production yet. It really sucks in terms of it's just a proof of concept, but I just want to show you visually the result of several iterations of TEXEL'S tuning working, sorry guys, with the evaluation parameters. So here I have the file called initialWeights.json, and this file serves as the input weights. By saying weights, I mean literally all the parameters from the evaluation function that affect the outcome of the game. Don't look at this one. This is not used. So only these p-square tables are used. Material weights. So downsides is for endgame, upsides for opening, and the very first within this material weights. So before the material weights, I have the margin for opening phase score, and here I have the margin for here is the margin for endgame score, and here I have the margin for opening score. The reason why the layout looks like exactly like this would be clear a bit later. So no hurries, please. Okay, and now I want to show the outcome, so the output after the several iterations of TEXEL'S tuning were done actually. So temp wait. So I've implemented the logic that when we have updated all the parameters within this 794 parameters, so when 794 parameters has been updated, well actually it's 794 minus 12, but it doesn't matter really now in particular. So when this let's say 800 parameters has been updated, so when all the p-square tables, all the material weights and the game phases, when all the parameters has been updated once. So this, by saying updated once, I mean every single parameter can be either be incremented by 1 or decremented by 1. Well, obviously this is the most naive and very basic, the most basic implementation of the TEXEL'S unit, but just for simplicity, and it really is because I don't yet understand more sophisticated ways of implementing this method, we'll take this one. So by saying one iteration, I mean that every single parameter could be either be like one higher or one lower compared to the initial result. And assuming that I have several sessions, I just want to show you them one by one, a few in the beginning and then the final outcome. Well, it's not yet the final, it could be running for 10 years more, basically, assuming the weird implementation I have and low processing capacity in my laptop. So it's not a point. So let's have a look. So this is the very initial, well, probably it's just probably be better to open in the new file. By the way, what I did, my Python script, so my TEXEL'S tuning is written in Python. It's independent from my engine. Usually people incorporate the TEXEL'S tuning logic into their engine, but in my case I wanted to make it separately so other people could be able to use my implementation in particular, despite the fact it's weird and all this stuff, but still it's just to play around with, at the very least trying to understand the concept of how it works basically. So as the output, my Python script generates JavaScript code, this one, that I can later just literally copy paste into my chess engine. So this is the JavaScript code generated by my Python script, and this is the output of the single iteration over all the parameters after TEXEL'S tuning method was applied. So then I just copy this then I can copy all this file, and I can just paste it right over in here. So just replace the previous one, just paste it here, and I can instantly run my engine with the new parameters. That's just a handy way of doing things. It's not essentially needed. That's just how I did, because it's handy for me. Okay, so just have a look. So have a look at the initial weights. Let's take just a very few weights in order to avoid getting tortured by all the majority of weights. So we have this values and this table. So we would be having a look only at the opening values of this first parameters. So we have these values, and here so we have increased the opening phase by 1, and also we've increased the bishop value by 1, rook value by 1, and queen value by 1. Not much. It doesn't really affect much, but this is the very first iteration, so just to bear in mind how the input data set has been changed after the first iteration. And then let's say it's more kind of seeing what's happening here on the pawn p-square table. So again, like, have a look at the initial. So it was 50, 50, 50 and many zeros, and after it's kind of like we have this values like being adjusted. So instead of having zeros on the board edges, it gave me like -1, -1 here, -1 here, which at some point, this is something similar to what I had in Ronald Friedrich's implementation. So we have this minus values on the board edges. Well, obviously the data set that I was training with is measurable. For this particular example, the number of position was only 1,000 of positions. It's very miserable, and it's producing really not usable results. But again, like I just try to make a proof of concept implementation here. I mean, like then I tried to run with a 10,000 positions to calculate mean square error for, but that's kind of too long. Well, so regarding the possible optimizations and my plans regarding how I'm going to be altering the TEXEL'S student to apply this to Wukong, it would be covered in the end of this video. So let's keep going with the method itself. So you see, like initial weights, the very first changes that has been made, and now let's have a look at. So here we have around 20, well maybe 15, I'm not sure. Let's say 15 iterations. So it means that every single parameter, well, let's just calculate them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, that's almost guessed that. So 16 parameters. This means that at this particular stage, after the iteration 16, the values of the parameters at very most can be changed by 16. So let's say this value was 50, the biggest value it can have like 50 plus 16, so it would be 60, oh my god, 66, right? Or minus 16, and I can't even calculate that in my head. So, well, obviously that's just the maximal number of how the value can get altered, assuming the current number of iterations so far. Okay, just want to drink a bit of a tea. My throat is a bit not that great now. Okay, so just to give you an idea, so you just have an overall visual look at the tables after 16 iterations. So here is how the initial weights look like, and here's how the 16 iterations over all the parameters when it was applied. This is how the data looks after. And again, like you see, like the night has been changed as well. So it's now the data is really different. Well, let's have a look at the bishop, the third one. So let's say the bishop, it's almost unrecognizable. It's kind of visually seems like completely totally different values. So now now in order to measure the accuracy of the results we have, we can simply run the tournament between two versions of our engines. That I think a hyperbole time control is fine here. So the first version, well, assuming the search in both versions of your chess engine in the same, you can use, let's say, this initial weights in one version of your chess engine, and then you can use this tune weights in another version. And these tune weights should result more elo points compared to the first version. So the version with this tuned values should be stronger. But again, like on the real deal, it really needs testing, and the matter of minimizing the mean square error doesn't always mean that your engine would be playing stronger, because mean square error is just is the bare statistics, and it might not always be representing the actual real outcome of the particular game your chess engine is playing versus another version or another engine, doesn't matter. So now when the input data and the output data is being declared, we already have the very first and the very last elements of the entire pipeline that I'm about to describe just now. So let's actually start. Oh man, so okay, so I just want to open the implementation itself. And again, like I'm going to create some sort of a, I don't know, probably documentation is maybe not the best ever word. So here is the evaluation tuner. So here is the implementation of the TEXEL'S tuner that I will now walk through. And just in order to, maybe it's not always easy to get this knowledge from the video, maybe it would be better to read them. So I have an idea in mind to create some documentation. Probably describing TEXEL'S tuning doesn't really make that much sense. It has been described already, well, maybe without those complicated formulas and using say Python code examples instead of this complicated mathematical formulas. It would be a good idea, but I would rather want to focus on the particular Wukong tuning when this, I didn't yet actually establish that. So as soon as that would be established, hopefully we'll make that sort of a documentation. Well, anyway, so you know, guys, just let me just start. I just feel a need to write, to type. I mean, because so empty. Probably this would be in the description below the video, or rename TEXEL'S tuning.txt. So I can even make it kind of bigger. So the very first thing we need to do, we need to obtain a training datasets. The word training, it's the machine learning term. This means the data that we're using in order to tune our evaluation parameters. So, bear in mind that the input data we're working with is these weights in particular. So obtaining training data set. There are various ways of how one can do that. Just to give you a couple of examples. So the training set could be generated from the self-play, where that's the original methodology of TEXEL'S tuning method. So say you can have different versions of your engine playing each other at hyperbolic time control, and then you use that PGN file to extract the positions to apply and to use them to calculate the mean square error. So just a little bit later about this. So the first, you can use the self-play, but in my case, I'm using the existing data. So the difference is, well, when you're using the self-play, this is known as the reinforcement learning, because you're learning from the data that is generated by your own engine. And for some reason, it seems like that using this, the games of the self-play is results better. Well, I can't say because they didn't really yet make that lots of testing. But on the other hand, the cool thing is that we can use an external data set, not produced by the self-play, but just whatever chess positions that we know how they result, and use them to train our engine. And that is known as the supervised learning. So these are two different approaches. As far as generating my own data set takes kind of too long, I decided to pick up an external source and go follow this so-called supervised learning approach. So this is the very first thing. And now I just want to show you how the data set looks like, because this is the very essential thing to consider. I have a very big file here. Well, obviously I'm not looping through all the positions, for in my case it would really take ages. Just to give you an idea, so this is 300 megabytes. And so how did I obtain this? I had a PGN file called gm2600.pgn with the famous chess games like Fischer-Spassky, like 60s, 70s, 80s, 90s. So really lots of strong grandmasters for a long time, basically, from the past, and probably some present as well. I'm not sure. So I was using not chess engine games, I was using human games. It's hard to say whether this is a good idea or not, but well, still it's still loading even within this text editor. So sorry, it just takes a little bit too long. So yeah, I would rather demonstrate. I would rather demonstrate this here. I have a minify. Oh man, I don't show you this. It's the minify version of 6 megabytes and 1 million positions, if I'm not mistaken. Let me just make sure how many positions there. Okay, tools. Yeah, this should be 1 million position. Yeah, it goes much faster. Still, it's gonna take ages to get to the end of the file, but it doesn't matter. So here is how the data set looks like. So it's no longer a PGN file, so we don't have moves here, but instead we have positions. So just to give you an idea how the positions looks like, so if I just copy the single position, and then, well, where's my Wukong? Oh, where's my Wukong? Hold on, guys, just want to open my engine to show you how the PGN, how the FEN looks like. Yeah, here. So let's say this position. A few notes on how to generate positions. This is very important. I will now cover it. So but first I just want to show you some positions. So they are randomized at the moment. So they are not like from one game, one position after another. It's totally randomized stuff here. So you can use this data set in particular. I will provide all the links in the description, obviously. Just to give you an idea regarding the positions, so this is how they look like. Oh man, what am I doing? No, I'm doing everything correctly. Okay, so just to give you a quick idea of the positions. So they're from different game phases, from the different material. It might be material imbalance. They're, let's say, different number of pawns, etc. So absolutely kind of random positions. But a very important part is to make sure that, well, it depends on whether you're using evaluate function to get the score of a current given position, or if you're using so-called question search, which helps to resolve heavily tactical positions with the forcing lines. Now regarding the very first optimization that even like me came up with, so instead of using question search, we can use simply the evaluation function directly. But in order to do this, we need to get rid of so-called tactical positions from the data set. And the way I did this in particular, and now we already come into the very first part of the source code that regards to TEXEL'S tuning, the generate data set. Oh man, just so many stuff is open here. Okay, I start from the very beginning again. So, okay, Wukong JS, yeah. So evaluation tuner.py. So here I have, well, just a quick idea. So this MVVLV is only needed for a move over into make questions fast. Otherwise, it takes ages to calculate the score for a current given single position. Just try it if you don't believe me. These are all the helper functions. Just needed to manipulate the input data set back and forth. I'll cover this later on. Doesn't matter that much. And this game phase score and evaluate actually evaluates the current given position, bearing in mind the evaluation function that I've just shown here. Let me just drop back to that. The evaluation function I've shown here. So again, like the reason why to consider Python. So, well, first, Python is faster than JavaScript. Second, Python has a fantastic library, Python Chess, that allows to manipulate, to parse PGNs, generate FENs from board positions. I don't yet have that functionality in my WukongJS chess engine. Probably I can't see much reason for doing that. So it's much faster to rewrite the evaluation in Python, and also to write the questions. I also need questions as well. In Python, it's just 2 functions, literally, and that's it. And this is much faster than if I was writing PGN parser in JavaScript from scratch. That's gonna be too long. So that's the reason why I decided to pick up Python. Another reason, so it's easier, it's kind of engine dependent at the moment, so you can just generate the values and then you can implement the simplified evaluation function, simplified tapered evaluation function, and auto-tune one. And then you can embed this to whatever engine you want. And again, like you see in the output data set, it just looks like a JavaScript like we have here. So it's not a big deal to convert this to Python, C, C++, or whatever language. So that's the reason of why did I consider Python. Okay, so the next thing, generate moves. So, okay. So this is the evaluation quiescence, and yeah, generate dataset. So what I do, I open the PGN file. I'll give you a link in the description below this video. I have this on my Google Drive, gm2600.pgn. Also have a thread on TalkChess pointing out to this sort of a data. Probably I can give a link to that as well. Then we loop over all the games. So it's total games, this number. Well, for some reason, maybe I was out of memory or some other thing. I didn't manage to extract the positions from all the games, but from these 3,000 games, I've extracted positions from about a half, a rough estimate of about a half, maybe 100,000 games or something. But for TEXEL'S tuning, it's literally enough to extract the positions only from 64,000 games. So it's more than enough. It's really more than enough here. So the next thing to consider, so this is just the Python chess specific stuff. I'm just initializing the chessboard here. So the idea is that the next stage, we need to loop over the moves within a current given PGN. So literally we play the move on the chessboard. Okay. Here I'm also calculating the move number to avoid storing the positions from the opening, which is one of the requirements of the TEXEL'S tuning itself. And then I also want to exclude the positions that where the checkmate is on the chessboard, because in that case, evaluation doesn't really matter that much. And now, regarding this line, bearing in mind the fact that I've created this on my own, I didn't copy-paste it from somewhere. So most likely can't be wrong, but I just want to explain the logic of what I'm doing here. So I'm comparing the score obtained by the evaluate function with the score obtained by the quiescence function. And if they are the same, and this is the most cases basically, it's not really that much technical positions. Well, anyway, it skips lots of them, but just that doesn't matter. We have lots of games and lots of positions, so generally it's more than enough here. So we're just getting rid of all the tactical positions. So, and this means that later on within the pipeline, adjusting the weights, instead of using quiescence as described in the original TEXEL'S tuning method, we instead can use evaluate, because the score obtained by the evaluate would be exactly the same as by the quiescence, but much faster, because we're just getting the static evaluation without actually searching anything. Okay, so I hope that's quite pretty clear enough here. And then, well, this try except is just because the encoding issues with the PGN file. And then we just append in the FEN string, and then we using the, I'm extracting the result of the game from the PGN headers, and I'm converting that result to the string representation of the floating point value. So this is like, so wins are converted to the 1.0, but this is stringified just to concatenate the string. Python requires that 0.5 to map the draws and 0.1 to map if the black wins. So once I heard the term probabilistic values, so these are known as the probabilistic values, like the probability of how likely white to win, black to win, or if it's a draw. But so these are the complete values. So this is the 100%, like white wins, the 100% it's a draw, and the 100% it's like a black wins. But these values would come into the stage just in a few moments later. Okay, so let's get back to the generation of the data set. So we append in these positions, and eventually we're obtaining this sort of a file, which is really big one. And again, like you can already skip these steps. Well, you can rely on the data set that I've generated. You can try your own. It doesn't matter really. I just first initially I try to use the data set from the one of the threads on the TalkChess. It's called Ethereal. This is the chess engine by Andrew Graham, for those of you who's not aware of that. So Ethereal data dump thread, and I saw exactly this sort of a format, like FEN string followed by the result in this square brackets. I really loved how the format looks like, so I decided to make the same here on my own as well. So here we just appending the we are appending this position to the file. Well, first not even to the file, we're appending this to the positions. Then before writing the writing this position to the file, we first randomize them. So we're shuffling the position within the single PGN game first, and then writing. And later, so when all this stuff is done, when this routine is over, then I was also randomizing the entire data sets, because if before that it was like 10 positions win, like 20 positions draw, like 30 positions win black, and so on. And now it's kind of maybe like 2 positions draw, 1 win, 1 lose, 10 draws, 5 loses, black wins, like 10 white wins, and so on. So it's completely random. So we just have a look at the results. You see like win, draw, lose, win, draw, win, draw, lose. So they are random. So it's not the positions like from one game. It's all the positions from all the PGN file in a completely random order. And this generally affects the accuracy of training process. And that's some sort of a required stuff to consider, basically. So this is it regarding the updating a training data set. It's a bit of a time consuming, and you need to put some effort in order to make this. But so let's say we did obtain our data set. Again, like also you can obviously play. You can generate data set on your own. Just make your engine play in versus itself for really lots of games, and then you use the PGN from those games that your engine was playing versus itself. That's it. Okay, so this was the very first step, and let's go further on. So the second step, I just want to show you this in the very limited example, and then you'll see how this example is extended to the entire kind of mechanism of this TEXEL'S tuning. So you just have a look at this outcome of the game. Now the position, it can be evaluated. So whatever position we have on the chessboard, we can get a score for this. This would be a scalar score. Well, let me just make a move. Well, obviously now its entire research was working here, and well, this value is kind of too big. It's not really that great, but anyway, we have a scalar value, and this is very important. So whatever positions, well, here I'm obtaining the score by actually making the full-blown alphabet search. In original TEXEL'S tuning method, we can make just a question search. In this optimized method, we can make only evaluate, because we've dropped all the positions where questions doesn't result exactly the same value, so the evaluate does. But anyway, we need to obtain the score. So here, I just roughly say evaluate, well, not evaluate position. Let's say get scalar position score. Or just say evaluate position, evaluate it. And now let's say the score is 25. Well, in this case, it's obviously like minus 712. Doesn't matter. Let's say that it's 25. The next step we need to convert scalar score to win probability. I'm sorry if I'm saying some nonsense here, or if I'm inaccurate in terms. I really suck in math, so let me just explain by hands what I mean by saying this. So as Ronald explained me, it's the very good term, we need to map values from 1 to 0, from 1.0 to 0.0. So let's say just an example here. So just an example. So let's say we have game result. So game result white wins. Okay, so we need to convert this to this kind of probabilistic value. I'm sorry if this is not called probabilistic or something. Just so this is converted to this. Let's say if this was a draw, it would be converted to 0.5. If this was black wins, it would be converted to 0.0. So it's the range. It's within the range from 0.0 to 1.0. So let's consider that we have this situation here, and it's converted to this sort of a value. Now the next step, we need to convert our this score to the scalar probability. The particular formula that is used in order to obtain this sort, it's called the sigmoid. It's not the standard sigmoid. It's a variation of sigmoid. If you just to give you an idea of the particular Python code that actually calculates this sigmoid. So where is my mean square error function? Yeah, this is the formula to convert, say, this value to, well, let's say score. Let's say, so we convert score to, so let's assume that after applying this formula, we will have the value of 0.75. And 0.75 is closer to winning than to either draw or even worse if kind of black loses. So let's assume that this 25, this is plausible, this is plus 25, right? So this means that white is better actually in this position. Okay, so now we've converted this value to this one using this sigmoid function here. Okay, and now we need to calculate the error, evaluation error. So in order to calculate it, we need to take the outcome of the game, so this 1.0, and say minus 0.75. This would be equal to 0.25. So here we have an error. Well, this is kind of like, probably this can be called statistical error. I'm not sure if that's the correct term, but we have this error for a current given single position. Well, let's say for whatever, for this one or for whatever position, we have this error. And now the next step is to calculate the mean square error. So in order to so get scalar position, convert scalar score to winning probability. Yeah. So let's say for calculate error for a given position, and then let's say repeat 1, 2, and 3 like the number of position. Let's say repeat steps 1, 2, and 3 as many times as many positions we have. So here I've described the process of getting the error for a single position. But in TEXEL'S tuning, well, if you're using some sophisticated optimizations when you can do it really faster compared to what am I doing, you can obviously use like 100,000 position, 1 million positions, so really lots of positions. In my case, I used the most number of positions I used was 10,000. So it's on you to decide how many positions to choose. It depends on the dataset quality, on many circumstances behind it. But well, generally, the greater number of positions you have, the more accurate results you're having. So literally this means we need to calculate errors for all positions. And then, so here is an example of how this for one position, so for single position. And then the next step would be to calculate so-called mean square error. It's done very simply. So we need to, so let's say we have the error 0.25 for one position. For next position that would be like 0.23. So we need to summarize all the errors. So this is done in the following way. So first sum all the errors, and the second step we just need to divide sum of errors by number of games. Okay, so we need to divide sum of errors by the number of games, and this is what is known as the mean square, as calculating the mean square error. So if you have a look at the implementation, particular one, so here we have a loop over all the positions for every single position. So here I have the error. This is the variable that is getting accumulated by the time. So I'm calculating error for I just forgot to say that so error is not calculated like this, but it's also needs to be squared. So I'm using the Python notation here. So it would be like this, because we have the mean square error. Okay. Yeah. So sorry, this is a little bit of a math stuff that I'm really not good at. So this is the error. So this error variable in this mean square error function, what it does, so it accumulates the error. So these values are getting accumulated, and at the very end, when we did loop over like 100,000 of positions, then we're taking this error and dividing this by the number of positions we were iterating over. So here, I was just limiting the entire set of FENs by the number of positions. So this loop only loops over this number, literally over this one. This is the very first attempt. 1,000 is very miserable. It should use at least 10,000, but that's not the point now. So this mean square error function returns the mean square error when all the positions were traversed, evaluated, and the error was calculated. So we have in the mean square error like for based on all of these positions. And now the most interesting thing, basically. The most interesting thing now, that we just have a look what values in particular can affect the mean square error. Those values are the evaluation weights, right? So simply saying, the more accurate values we have in these p-squared tables, in material weights, in opening and endgame, in game phase scores, the more accurate values we have, the less error we have. So this means like these values, like from the statistical perspective, from the probability perspective, they kind of correct in terms of they represent the outcome of the game. So in perfect world, these values would result always win, but obviously it's impossible. But just to give you an idea, so after calculating the mean square error, okay, and I just want to say that the mean square error depends on the particular values of this evaluation parameters. So if we just drop the if we just drop the automated part of the TEXEL'S tuning, let's imagine the TEXEL'S tuning is the manual tuning, kind of like, right? So in that case, we just calculated the error, and then let's say just, I don't know, I'm just manually changing the values, and then I'm trying to recalculate the mean square error again. And if the recalculated mean square error is minimized, that means that the new values that I've entered here are better. But obviously you won't be doing this thousands of times by hands, right? So there, you just need to write some sort of a routine that would be doing this automatically for you. So the idea is, and now I'm coming to explanation of the most simple way of how to adjust the weights of the evaluation parameters within the TEXEL'S tuning method. So the idea is very simple. So we need to loop over all the parameters of the evaluation function. Now, to make it easier, that's the reason why my input dataset looks exactly like it looks like, because it's just easier to loop over those values. So let me just show you this. So I'm taking the weights from this JSON file, and the reason why they mapping all together is just because I can loop over two phases, and then within these two phases I can loop over all the values. So it's almost like iterating over all of these values, which are the evaluation parameters, within a single loop. If we have a look at the implementation, this is known as the naive way of TEXEL'S tuning, the slowest but at the same time the easiest way of doing things. So here is the function called tune. Yeah, this is it. So the very first loop generally says, as long as we minimize the mean square error, we want to repeat the process of adjusting all weights and do it again. But on practice, as mentioned by Ronald, well, let's say he had 40 iterations of his TEXEL'S tuning routine running, but let's say after 40 iterations it doesn't result a greater elo points anymore. So the matter of minimizing the mean square error doesn't always mean that the actual plane strength of your chest engine would be increased. It's not always like this. So you can't blindly rely on this statistical results. You also need to make sure that you're testing newly tuned values versus your previous version, and only in case if it performs better, in that case you can keep those values, and then you can apply TEXEL'S tuning to already tuned values. So that's the idea. So the next thing to consider, we need to loop over all the parameters within the evaluation function. And well, here I just skip material for black, just because I don't really want white pawn have different value than the black pawn, because that would result, statistically it might be true, but on practice that would be result in the weird behavior. And then what we do, so here I'm creating a new copy of the input data set. So I'm literally creating a copy of this weights, not all the objects because it's also used within the evaluation, but only this weights key value pairs to this weights. So I'm literally making a deep copy of this. So in order to make a deep copy in Python, I'm using JSON loads, JSON dumps. And well, initially I'm storing the input weights. This weights initially I'm storing to so-called best parameters. Then I'm creating the new parameters, which is the deep copy of the best parameters. And then within this deep copy, I'm adjusting the value indexed by the index. So literally, I'm adjusting this value, and then this one, and then this one, and every time. So I increase the value by 1, and then I need to recalculate the mean square error. And now, if the new error, so this is kind of new error. So if the new error is less than best error, so if this updating the parameter by 1 minimizes the mean square error, in this case I'm updating the best error and the best parameters as well. And this means that we have improved, which means that we can longer go within this initial loop, but that would be not that fast really. Otherwise, if this doesn't work, we need to decrement value by 1 at exactly the same for the same parameters. So say we try 5601. It doesn't well, if it does minimize the error, then fine, we just skip it. and we go to the next parameter. If it doesn't minimize the mean square error, then we try 5600 minus 1. This would be oh my god, it's too hard to calculate. Let's take this one. So let's say we try 101 and it doesn't increase the it doesn't minimize the mean square error. Then we try 99, and let's say 99 does minimize the mean square error. In this case, we keep this value, and then exactly the same stuff is done for every single parameter. This means that within this current within this loop over all the parameters we can, so this is known as the session, the single session of well, probably maybe it's not really good idea to call it a session, but let's say the loop over all the parameters. So within the single loop over all the parameters, the value that current given parameter can be changed by is only 1. So it can be either plus 1, either 1 greater by 1 or lower by 1. And if, well, let's say this eventually becomes 330. So in order to make this possible, we need to run at the very least 30 loops. I hope it now gets clear why exactly this is like so. So this is the most easy, this is the easiest and the slowest method of how TEXEL'S tuning actually working. So let's move further on. So yeah, so literally I've explained everything here already. All the other functions here are just a helper function. So this store ways allows me to actually generate the JavaScript code that I can later on embed into my chess engine. So it's nothing complicated, no rocket science here. Updating weights is just the logic to update. So the idea is that the weights that actual evaluation function within this Python script is using should be updated. So it's not the matter of updating the file, obviously. So we're just using the file to initialize the internal parameters of the evaluation. Then we updating the internal parameters evaluation, and then we need to extract these parameters back to calculate this mean square error, because the format of the weights used, well, actually, no, I don't even remember how to make it. Yeah, the format is the same, but I'm using some additional mappings to make the evaluation code simpler and more readable, basically. So I'm mapping the indices from the weights to, but it doesn't regard to TEXEL'S tuning, basically. It's just the technical part of how to implement the manipulations with these weights. So here, yeah, I'm just mapping the p-square tables to the specific indices within the weights lists that I'm getting from the input file, but it doesn't really matter that much at the moment. So literally this is it, believe it or not. So where did we stop? So calculate the mean square error, and then we want to adjust weights. And I just roughly say this adjust weights because the particular algorithm to loop over all the weights and adjust them and increasing them by 1 or decreasing them by 1, the most slow is the most weird, then the most inefficient way of doing things, but very easy to understand, and even me can understand that, so that's a good idea for me, basically. So that's kind of it. Adjusting the weights. Also, people adjusting weights using so-called gradient descent algorithm, which is complete total rocket science for me at the moment. Well, maybe if Ronald Friederich would explain me how the gradient descent works, maybe in that case I would be happy to understand that. Well, that's completely totally different story. It doesn't, like the matter of how exactly you're adjusting the weights is not the actual matter of TEXEL'S tuning method. So it would say about the TEXEL'S tuning, its core just essence of what it is. It's the matter of calculating the mean square error based on all of the positions we have within our training data set. And then we just need to adjust the weights and then recalculate mean square error. So here I say recalculate mean square error. And here I can say that we repeat steps 7 and 8 until engine strength increases. That's it. So it's very, very simple. So this is it basically. And again, like as I was already mentioning, that the matter of mean square error getting minimized doesn't always mean that your chess engine's strength would be increased, because just bear in mind that this is the statistical method, and as my client, who is a data scientist, he told me that trying to apply linear statistical algorithms to completely non-linear processes like the game of chess might be resulting in weird results. But on practice, TEXEL'S tuning is quite pretty effective, according to lots of chess engine developers reported that they have success with this. So this is it. Let's quickly walk through the steps again, and then just a little bonus at the very end for those who are still with me, because I have no idea how long this video launches at the moment. It's probably too long, but anyway. So we need to obtain a training data set, either from self-play or just take it from somewhere. Then we need to extract the set of positions that looks like this. Position followed by the outcome of the game, so result of the game. Absolutely essential, very important. Then we need to get the scalar value, the scalar score of the position, either by using the evaluate function or the question search. If we use an evaluation function, we need to make sure that no tactical positions occur, or otherwise this means that the score returned by the evaluate is equal to the score returned by the questions. Okay, so the next step to consider, we need to convert the this like scalar score to what I call winning probability. I might be wrong in the terminology here, but the idea is that we converting this value to this like value, which maps between 1.0 and 0.0. In order to do this, we need to use what is known as the sigmoid, and sigmoid is calculated using the particular formula. Oh man, where is that formula? Here it is, using this formula. Okay, this constant is known as coefficient, and smart guys like Andrew Grant, the author of the Real Chess Engine, have a very rocket science explanations on how to calculate this. I just grabbed the constant from Minic Chess Engine by Vivienne Glazon. I'm not sure the last name of the guy. So this just might be working, and just that's just fine. So this is how so this formula converts this like value to this like value. Okay, then we need to calculate the error for a given position. This is how it's done. So we take the outcome of the game, and we need to subtract the win probability, the scalar score converted to the winning probability, and make it square. I'm sorry, my English is too poor to explain this. I don't know how this calls correctly. So we need to square this. I don't know how to call it. So this is also like maybe like this, but from the programming perspective, this is the XOR operator. So in Python, what I'm trying to explain, this is done like so. Okay, and then we need to repeat these steps. So step 2, get the position, evaluate the position. Step 2, convert to the win probability. Step 3, calculate the error. So we need to repeat this the number of times of as many positions as we have. Then we need to, and every time we're doing this, we're summarizing the error. So error of one position for another, and 1,000 100,000 times of that. So we accumulating the error altogether, and then we dividing the error by the number of games. So calculating this is known as the calculating of the mean square error, summarizing all the effort, all the errors divided sum of errors by number of games. And this function is very simple. It's available right over in here. Then we need to adjust the weights. Again, like there are really numerous ways of doing that, depending on how smart you are. The most trivial and so-called naive way, we just loop over all the weights. We increase value of the weight by 1, then we're recalculating the mean square error for it, waiting for ages until it's done. And if it's better, we store it. If it's not better, then we want to decrement it by 1. One little implementation detail. So by saying decrementing by 1, it might be a little bit confused by this sort of stuff. So here we say plus equals, well, adjust value. I'm using the variable here because I was playing around not only 1 but some greater values like 5 to obtain the very initial weights. About this a little bit, just hold on about this just for quite a bit of time. So let's say plus equals 1, but here we doing so this would be like minus equals 2. So here we have plus equals 1, and here we have minus equals 2. Why? Because minus equals 1 would return the value to its initial state, and obviously this won't result in a greater in the minimized mean square error, because the mean square error would be exactly the same as we did before as we did initially. Initially, we also calculated the mean square error. This is known as the initial guess. If you say, have a look at the complicated sources and complicated implementations of TEXEL'S tuning and engines like Minic by Vivian Clezon, you can see the word like initial guess there. I couldn't understand what the heck that means. So this is what it means. So just calculating the initial value of the mean square error. That's pretty it. Okay, then so we need to say minus equals 2. So let's say if the value was say 5, then 5 plus equals 1 would be 6, and then we want to, so 6 doesn't work, so we want to try 4. In order to get 4, we need to say 6 minus equal 2. Okay, so that's how it's done. And then we need to recalculate the mean square error again. So in case if the weight adjustment makes sense, by saying makes sense, I mean the mean square error getting reduced. In that case, we're storing the newly updated adjusted weights and going to the next weights. Well, anyway, we go to the next weights regardless of whether the current weight has been adjusted or not. It might be that the weight is not getting adjusted for several iterations, and then it just gets adjusted. That all happens because the hidden interactions between the evaluation parameters, they heavily rely on each other. And again, like this sort of a tuning is like the most simple way to reveal these interactions. So I hope that's clear. So again, like recalculating the mean square error, and then we doing this adjusting weights for all the evaluation parameters, recalculating mean square error after every single parameter has been changed. So we're doing this, we're repeating these steps, well, ideally until mean square error is no longer getting minimized. But from the practical perspective, you need to make sure that you might find yourself in the situation when the mean square error is still getting minimized, but it doesn't result a stronger play of your chess engine. So let's say after around 20 or 40 iterations over all the parameters, let's say we loop over like 800 parameters once, we loop over 800 parameters twice, 3 times, 4, 5, let's say there was 20, and then we can just take the version where we did iterate 20 times, play it versus the version that versus the initial data set to see whether it makes sense. If it does, then we continue this work further on. Let's say then we have the 40 iterations. Again, like try to play the version that had 40 iterations versus the version that had 20 iterations. And if it's better, then continue. And let's say then we have the version that has 60 iterations and playing with a version that has 40 iterations. And despite the fact the mean square error can be less in the 600 iterations version. It doesn't always mean that the 600th iteration version would actually beat the 40 iterations version. So it might be on the contrary. So make sure to make many tests. And again, like just programming is all about testing basically. Oh my god, guys, I can't believe that I finally explained my code against understanding of the TEXEL'S tuning method. And now, as a bonus, at the very end of this video, I feel pretty exhausted and tired at the moment because probably I was talking too much and the foreign language at the same time. So my wife is going crazy in the room nearby, so she's probably gonna kill me quite pretty soon if I don't shut up in the nearest 10 minutes or so. So just very quick bonus regarding my plans on tuning Wukong JS. I have a couple of ideas. So the first idea, which is possible, I asked guys from TalkChat, so they say that it is possible. So we can use all the 0 values, and still TEXEL'S tuning should be working for them. Now, what I want to do, I want to use the 0 values. I want to change the value for updating evaluation parameter from 1 to say 5. And to minimize the number of games to calculate the mean square error, because just to have a faster results. And in theory, I'm not sure how in particular this would be working, but I just want to obtain the data set that looks like my initial data set, but not taking this from head, but instead trying to take this from the TEXEL'S tuning itself, but say incrementing not by 1 but by 5. So you see, like these values are actually like incremented by 5 here, right? And then when I will have this data set obtained by TEXEL'S tuning from scratch, I can run the more kind of fine-tuning test, fine-tuning stuff to tune the values even better. So that's one of the ideas that I'm going to be trying to use within WukongJS. Again, I'm too dumb to implement gradient descent at the moment, and bearing in mind the fact that the very 10,000 even 10,000 positions to get the mean square error is too little value. So I don't know, probably I would be running 5,000, which is something in between 1,000 and 10,000 to actually to get the final weights. So I'm not sure how stronger my engine would be compared to like values taken from head. Most likely it would be weaker compared to the values obtained by Ronald Friederich that are used in WukongJS just right now, basically. The values I've been showing you are just okay, forget those values. So yeah, that's pretty it. Probably it would be weaker, but at very least this would be absolutely my own values, and the most benefit of this that I would be totally understanding how in particular I got those values. Okay guys, this is it from my side. I can't believe this video is coming to the end, and I really wish you all the best basically. By the way, in my country Christmas is today. It's not on 25 December, so probably don't really care much about that, but I can congratulate you with this holiday as well. So wish you all the best. Have fun with TEXEL'S tuning. I hope now, if even noob like me managed to implement the very naive implementation of TEXEL'S tuning, that you guys much smarter than I am, you will definitely be able to make this on your own and have fun with automated evaluation tuning. This is from my side. Until the next time, and take care.